Here's the answer key to the Chapter 1 test. Now, feel free to fast forward this if there are questions toward the end that you missed, and maybe you don't need to look at some of the ones in the beginning. Now, with this first question, you would have gotten one of these three. So you didn't have all of them. You would have just had one. They're all the same concept, just reading a graduated cylinder. But you can use the other ones as extra practice if you missed this one. The first graduated cylinder has markings every milliliter. So we would have estimated the tenths. So it's maybe like right underneath the 45. So 44.9 is the only thing reasonable. If someone picked 40.5, they misread the markings. That those individual little markings are the milliliters, not like the tenths of a milliliter. The second and third graduated cylinders are marked with tenths of a milliliter, so we can estimate the hundredths. So the one in the middle looks like about 4.8, and maybe here like 4.80. It's really close to being right on the line. If you were manually measuring, maybe somebody said 4.79, something like that. The last two choices do have proper Sig Figs, but they either didn't estimate reasonably. Like 4.88 would be really close to 4.9, which it's not. Or 4.08, again, they misread the markings on the cylinder. And then the third choice, the markings are the tenths, so it's somewhere in between the 8.4 and the 8.5. So yeah, like 8.46 seems reasonable. You would have had one of those three. This one I think everybody had. The graduated cylinder that would give you the most precise measurement gives you the most detailed, or the most decimal spots. So that should be the second one. That one is marked with each tenth of a milliliter, so I can estimate to a hundredth. All of the other ones have markings every milliliter. With this one, again, you would have had one of the three, but there's extra practice if you need it. With metric conversions, we should be familiar with like kilo through milli, and we should know like milli means 1,000th. There are 1,000 milliliters in a liter, or a kilogram is 1,000 grams. It takes 1,000 grams to equal 1 kilogram. We should be familiar with these units in green. Yeah, there are other metric units, and we'll use them when we need them. There's mega and giga and pico and nano, and we will use nano in a couple weeks when we talk about like wavelengths of light. But if we have to do a conversion from nanometers to meters, we'll just deal with it at the time. We'll look it up. So I would kind of make sure I'm okay with the metric units in green. The first one gives me milligrams to grams, so I wrote that one in red. I would start at milli, and I'm going to move it back 3 places to get to my base unit, which would be like grams, meters, liters. So I take my decimal spot and move it backwards or to the left 3 spots. Now, if one of the choices would have been 0.000056, that would have been fine. I mean, the second choice is close. It's just missing some zeros. But that wasn't one of the choices, so we had to go with then 5.6 times 10 to the negative 5th. Similar with the one in the middle, I did this one in blue. It was another milligrams to grams. So I'm going to move the decimal spot to the left 3 places. And so it's going to go backwards to the left 3 spots. If 0.0003822 was a choice, that would have been great. It was not. So instead, the answer with the scientific notation is totally acceptable. 3.822 times 10 to the negative 4th. And often we use scientific notation for numbers that are really small, or like in the third choice, a number that ends up being really big. This was grams to milligrams. So I did this one in orange. Now I'm starting at the base and I'm moving forward or I'm moving to the right 3 spots. So in orange, then, if one of the answers would have been 5,687,400, that would have been fine. But it's not one of the choices, so then we would go with the last option. Same number, it's just in scientific notation. Cool. So I should be able to do some basic metric conversions. You would have had one of these 3 just on measuring how many significant figures are in a given number. So the first choice, 19.0, if there is a 0 at the end of a number, it's significant as long as there's a decimal spot. So 19.0 would have 3 sig figs. Any leading zeros are not significant. So anytime a number starts off with 0.0000, it doesn't matter where the decimal spot falls in that mix. Any zeros that lead off a number are just placeholders, and they are not considered measured zeros. And so the 0.006 only has 1 sig fig, just the 6. In scientific notation, anything out in front of the times 10 to the whatever power, that's what they mean to be significant. So in 1.60 times 10 to the 8th, it's 3 sig figs, the 1.60. Because again, there's a 0 and it's after a decimal spot. So that is significant. But then like in choice 4, 13,600, if there are zeros at the end and there's no decimal spot, then it shows that the number was rounded. Maybe originally it was like 13,612, and for some reason I needed to round it to either 3 sig figs, or I wanted to round it to the nearest 100. Then I just don't put a decimal spot at the end. So just the 1, 3, and 6 are significant. If I do mean for all those zeros at the end to be part of the measurement, then you'd find a decimal spot. So 100, boom, with a decimal place, that's 3. So of these 5 choices, there are 4 that have 3 sig figs. And they're all really similar. The middle choice, 19.00, would be 4. 0.0006 just has 1 sig fig. None of the leading zeros count. In scientific notation, anything out in front of the times 10 is significant. If there are zeros at the end with no decimal spot, they're not significant. So in that 4th option, 1,360 is just 3 sig figs, not the 0. And trapped zeros in the middle of a number are significant. So 10.05 is all 4. The middle choice, how many had 4 sig figs? There were 3. And the last option, 19.000, has 5. I don't care how many zeros are out in front of a decimal, or out in front of a number, whether they're before or after the decimal spot. If they lead off the number, they're just placeholders. So in that second option, just the 6. Anything out in front in scientific notation is significant. And we would count the trapped 0 and the 0 after the 9, since there is a decimal spot in the number. But 13,600 is only 3 sig figs. And again, 100 with a decimal spot is 3. So this one asked how many had 5 sig figs, so there were 2 options. You would have had one of those 3 questions. And same thing with this. I think sometimes we just misread this one a little bit. It's giving you 2 numbers, and it says the sum of these numbers has blank total sig figs. The product of these numbers has blank total sig figs. Okay, so when I do adding and subtracting with sig figs, you plug it in your calculator and you round it to the piece of data with less decimal spots. Decimal spots. So when I add this in my calculator, I got 33.271. But now when I look at the decimal spots in my 2 given pieces of data, I should round this to the lowest number of decimal spots, would be 2 decimal places. But then my final answer would be 33.27. And the question says how many total sig figs? 33.27 has 4 sig figs. Oh, I think sometimes people kind of misread that and they picked the last choice and they were like, oh yeah, when I add, I'm looking for the lower number of decimal spots, 2 decimal spots. Oh, you were so close. But it said like how many sig figs would be in the sum. But now when I multiply, I'm going with the lowest number of total sig figs. And so now you could plug it in your calculator if you want to. I got 224.67642. But I would round that off to 3 sig figs. The 9.42 only had 3 sig figs. So if I needed to, I would round that to like 225. The 6, I would round the 4 up. Oh. And then the other ones, again, are really similar in concept. So when I add 18.82 plus 6.4 on my calculator, I got 25.22. But I should round that to 1 decimal spot. When I add, I go to whatever piece of data had less decimal places. Now, the product is actually kind of interesting. So when I plug this in my calculator, I got 120.448. Well, if I look at the pieces of data, I should be leaving 2 sig figs. The 6.4 has 2 sig figs. And so just for funsies, it's going to have 2 sig figs. But how would you do that? Well, you'd have 2 options. You get 120.448 in your calculator, but we can't create all this precision just as a result of a calculation. It's got to be a number that I can go in the lab and reasonably measure with the same measuring tools that I used to measure the original numbers. And so I could reasonably measure 2 sig figs. In this case, your 2 options would be to either leave it as 120 but don't put the decimal spot in, or go scientific notation, 1.2 times 10 to the second. Oh, either are totally acceptable, and then you've kind of simplified a bigger number down to a small amount of sig figs. And then the last choice, when I add, I get 28.42, but according to my data, I should only go with 1 decimal spot, the lower number of decimal places. That would leave me with 3 total sig figs. My final answer for the sum would have been 28.4, 3 sig figs. The product ended up being 109.956, which again, this one's kind of funky because if I look up my data, both pieces of data had 3 sig figs. So if you try to round this to 3 sig figs, you're looking at 110, but then how do you show that you want all 3 of those figures to be significant? Well, you either put the decimal spot at the end, 110 with a decimal place, or throw it in scientific notation and leave 1.10 out in front. Good stuff. So you would have had one of those 3, but it's great practice. And then here was our last multiple choice. So I think sometimes with this one too, we just didn't get the gist of the question. It's a measurement question and a sig fig question in terms of adding. So we've got 3 different beakers, and then we're going to pour the contents of each beaker into an unmarked container. So like no graduations to measure volume. What would be the sum of the volumes reported to the correct number of sig figs? So first we have to make the measurements. First we have to make a proper measurement for each beaker, taking into consideration the fact that the markings are different. So if I start with the first beaker, the markings are every milliliter, so I can estimate to a tenth. So I don't know, I just estimated it's a little less than halfway. So like 26.4 maybe, somewhere in there. The middle beaker only has markings every 10 milliliters, so I know for sure it's beyond 20, but then the ones place is my estimate. So then I said, yeah, it's like a little over half, 26. The third beaker has markings every 10th of a milliliter, so I know for sure it hits the 26.4. And then I kind of just estimated, it's just a little bit above, like maybe 0.42. So first thing I had to do was make proper measurements. Now I have to add them together with correct Sig Figs. So the measurement in the middle has no decimal spots. So my final answer should have no decimal spots. This is a good AP kind of question and it's not a surface level question. Like, I don't know if I would give this to a first year kid, because there's like a lot going on. But I got to make my measurements correctly, and then I have to be able to add and round correctly. So 79, no decimal spots. Tricky, huh? All right. Then that brings us to the free response. Now, there were 3 different free response questions. 90%. They're almost the same. There's one little thing that's a little different, and I'll show you when we get to it. But most of it was the same. They all asked you to sketch a little portion of a graduated cylinder that can measure 40.0 milliliters. And so 40.0 should just mean that there's a line for every milliliter, and the tenths are the estimate. So the last spot, the 0.0, the tenths, that was the estimated decimal spot. So there's a marking for every milliliter, which maybe then you kind of figured out when you looked at number 2, because then they gave you a portion of the graduated cylinder, right? And somebody is looking to find the density of a plastic sphere. So on an electronic balance, they measured the mass of sphere A to be 8.186 grams. The sphere is added to the 40 milliliters of water in the graduated cylinder mentioned above. A portion of the graduated cylinder with the water and plastic sphere is shown below. Calculate the density. Okay, so we got the mass. Density is mass per volume, but it's per volume of the object. So like one of the most common errors was that people read this second graduated cylinder and yep, the markings are the same, so that's like 43, and I just said 43.0. It looked to me like it was right smack on the line. And so one common error then was that when they did their density calculation, they put 43.0 in the denominator for volume, but we want volume of the object. So the original volume of water was 40 milliliters, and now with the object it's 43. So the sphere had a volume of 3.0 milliliters. And it's important to say 3.0. If I'm reading the cylinder properly, there should be an estimate in the tenths, even if it's 0. Because then when I put 3.0 into my density calculation, that ends up being the piece of data with less sig figs, and then I would round my final answer to just 2 sig figs. Now, if you left it as just 3, you wouldn't have gotten full credit because you didn't make the measurement properly. But then if you did the calculation with just 3, then you would have to round your density to just 1 sig fig. And we have to use proper units. So you had to use the grams per milliliter. Every numerical answer should be rounded properly, and it should have units. Cool. All right, so the only thing that's different about the 3 different versions of this last question was just the mass of the cylinder. So if you're freaking out right now because you're like, my mass wasn't 8 grams, hang tight, I'll get to you. But everybody had the same question 3. So now using the same procedure, the student wishes to determine the density of plastic sphere B. So it's a different plastic sphere. But this time the sphere floats in water. The student uses a stirring rod to completely submerge the plastic sphere underwater. So I tried to kind of draw that up above in my number 1, my graduated cylinder. So if that red circle were the sphere, so if that were sphere B, and if it floated, then they took a graduated cylinder, a stirring rod, so that red line at the top is supposed to be a stirring rod. And they like poked it under the water. They're like, yes, we got this. The problem is, when the final volume reading is measured, some of the stirring rod is also submerged underwater. So like where I wrote that orange circle up on my graduated cylinder, that's a portion of the stirring rod that's still underwater. And so the change in volume is going to include the volume of my sphere and that volume of the little portion of stirring rod that's in the water. So it's going to seem as though the volume of the object is too high because it includes the stirring rod, which then if my volume is too large in the denominator, that's going to make my density too low. Now, one common boo-boo was that people said something about the mass will be too high because the mass includes the mass of the stirring rod. And I think not mass, volume. When you have this setup, when you put the sphere in the water, you're not finding the mass of the sphere. That would have been done on an electronic balance. So as long as I didn't put the stirring rod on the balance, it's not going to affect the mass of the object. But the stirring rod's going in the water, and that's how I'm measuring the volume. Aha. And then finally, number 4 was to convert your density from part 2 from units of grams per milliliter to pounds per liter. So this would just be a little dimensional analysis. And you could have set it up different ways. I kind of like the proportion stuff because it just makes me feel like stoichiometry, and I can't wait to do stoichiometry. But I also think it helps to kind of think of like grams per milliliter is like grams per 1 milliliter. And so first I set up a proportion where I wanted to cancel grams and then bring it to pounds. And often when I set up my stoichiometry or I set up my conversions, I put the units on the line first. I started with grams on top, my 2.7 grams. So to get grams to cancel, I put it on the bottom. What I want goes on top. I want it in pounds. 1 pound for every 454 grams. Then I canceled my grams in orange, and then right now my unit would be pounds. I've got the right mass. Then I got to work on the volume, and this was the more common boo-boo. Milliliters is starting in the denominator. So if you wanted to cancel, you have to put it in the numerator. Oh. So that milliliter needs to go on the top of the proportion and liter on the bottom. And then I put in the conversion. There's 1,000 milliliters in a liter. In the end, then I canceled my milliliters in green, and the only units left were the pounds per liter. So just be careful of that when you want it to cancel, your units have to be on opposite sides of a proportion. Sweet. And you can keep 2 Sig Figs because we don't need to round Sig Figs to any of those conversion factors. So if my original measurement was the 2.7 grams per milliliter, then I can keep 2 in my final answer. Awesome. Okay, so the other versions, questions 1 and 3 would have been exactly the same. You just had a different mass in question 2. And so that different mass would have given you a different density, and then that would have been converted in part 4. Same setup in part 4, it's just a different number. Or the other option for mass would have been 6.845 grams. Same setup, same calculations, just a different mass. And so this gives you, I think, extra questions if you just want to look at some for more practice. The retake would be really, really similar. It's obviously the same concepts. It's still 6 multiple choice and 1 little free response. That's kind of similar. So hopefully this helps. But if you find anything that you're still a little shaky on, then reach out and let me know.